Hey everybody, it's Mr. Allred again. I'm here to talk about P-series convergence and divergence. And up here, up top, I've got a little information about what we're looking at. P-series is basically the summation of the 1 over n to a power series. So this could be 1 over n squared or 1 over n cubed. So if we have something that looks like that, we can talk about basically the exponent and decide if it converges or diverges. So it says it converges if p is greater than 1. So what that tells us would be something like 1 over n squared, 1 over n cubed, 1 over n to the fourth, and so on. That would be a series that converges. Diverges if we use an exponent of 1 or less. Just off the top of my head, if p was 1, we'd be talking about 1 over n, which would look like 1/2, 1/3, 1/4 if we wrote out the terms, which we'll see in a moment, and we'll see why that diverges. But if you used a negative exponent, that would bring this up top, which would start giving you big numbers. And if you use square root makes a number smaller, but if you make a denominator smaller, you actually make the fraction bigger. But if you see something like this where you have n or x to an exponent that's fixed, you can use a simple rule, but I wanted to give you a chance to see why down here. So, without my head getting in the way, here is 1 over n. And the summation of this 1 over n, which is called the harmonic series, actually just keeps growing, so the summation goes to infinity. In this case, p is 1. And I've actually written some of the terms of the series out here. 1, 1/2, 1/3, 1/4. I've got them kind of color coded here so we can kind of see why it keeps getting larger. So basically 1 is 1 itself, and these next three numbers, 1/2, 1/3, 1/4. If you add those together, you get a number bigger than 1. These green ones, 1/5 all the way up to 1/12. If you add those together, you get a number bigger than 1. And basically the rule here is, or what's happening is, I can add enough of these fractions together that I can consistently start getting a series of summations that are bigger than 1. So what we've got right here out of these first 12 terms is something that's bigger than 3. Now, it would take a lot more terms to continue and have a sum of 1, but if we add enough of them together, we're going to get larger and larger numbers. If I have 1/1,000,000th and I add 1,000,000 of those together, I get 1. So if I add enough small numbers together, depending on how small they are, the sum can keep getting larger. We're going to talk about the integral test a little bit later in another video. This can also be proven with that, and I think we might. A different example here of another p series, 1 over n squared. Here the p is 2, so from that definition up above, this tells us the series converges. So I wrote out the terms here: 1, 1/4, 1/9, 1/16, 1/25. So these denominators are all perfect squares. You could try and add these up, but what I've got down here, I can't find or make a diagram that kind of really describes what I'm trying to do here. So let's kind of just stick the 1 off by itself. Let's kind of put it over here in a block. But 1/4 is less than 1/2. 1/9 is less than 1/4. 1/16 is less than 1/8. 1/25 is less than 1/16. This here square down here actually shows you why a geometric series converges. Okay, but seeing as how all of these are less than the terms in this series, we're still going to have some space left in here. So we'd get 1 plus something that would be less than 1, because we're just keeping basically a portion of the previous one. So it does not accumulate to that large amount as we talked about up here. So it kind of seems like the same thing. We're adding a bunch of smaller numbers together, but they're not getting small very quick. They're getting small slowly. And that means that there's not much difference between them, so they can accumulate to large amounts. Whereas down here, we're adding a bunch of numbers that are getting smaller, but they're getting smaller in terms of much quicker. they're not even a portion of the previous number. They're even smaller than the portion. And that way we don't get to even add anywhere near the previous. So in this case, this right here does have a sum. It converges. We just haven't seen what it converges to. That's not what a P-series test is for, is to kind of tell us whether or not it converges. And in another video, we can also show this through the integral test, but I just wanted you to kind of see a visualization of why these work outside of the integral test. All right.